Hello everyone, welcome to my Your Programming Club. Today we will be solving another daily lead code problem, and today's problem is also similar to yesterday's problem in the way that here also you are required to generate subsets. Okay, so we will be using the similar approach uh, like the one we used yesterday. And if you missed that video or solution walkthrough, then no worries, I will again be explaining the whole process or the whole intuition and how to think about it in this video itself. So without further delay, let's begin with the problem, reading with the problem statement. So you will be given an integer array nums of unique elements. So you have to return all the possible subsets. Okay, those of you who do not know what a subset is, a definition is being provided by the problem statement that a subset of an array is a selection of elements, possibly none of the array. Okay, so you pick some elements out of the array or possibly zero elements, then that is called a subset. Okay, and collection of all the subsets is called power set. So you have to return the collection, or in another words we can say power set. So the solution set must not contain duplicate subsets. Okay, it is to be noted that solution set should not contain duplicate subsets. I mean, it will obviously not contain duplicate subsets if you are picking each element only once, as per the definition of the subset. Because all the elements in the array are given to be unique. So there is no chance that if you are generating a valid subset and it being, you know, a duplicate subset. I mean, you can repeat your choices, then it would result into duplicate subset. But if you are always making unique set of choices, then it will say unique subset. Okay, so this is how you will maintain the uniqueness of the subset and return the solution in any order. So order does not really matter here for solving this particular one. And as far as the constraints are concerned, the length of the nums array that will be given to you is, you know will be of order 10, and each element will be ranging from -10 to 10. And it is said that all the numbers of nums array will be unique, as previously mentioned in the above statement also. Okay, so I will tell you how to think of solution for such questions and how to quickly solve it. So most of the time, there is a subtle hint in the, you know constraints or the size of the input. Here you can see that there will be only 10 elements in the nums array, okay, at max. So there is a little concept that we can use of, or because of that constraint, the input size being so less. So what is the concept? The concept's name is bit masking. So this is just a fancy name. What is the simple logic behind it is, let's say you are given an array. Let the array be A, B, C, D, and let the indices be 0, 1, 2, and 3. Okay, so if these are the indices, then let's say what is the maximum range of indices we can have? It can go till, you know 9. Okay, so in total, number of how many numbers will be required if you want to form a mapping of these indices with something? What is that something I will be telling you? So you know that in a integer type variable of 32-bit, there are 32 bits. Okay, and how many, if let's say I do a mapping of this zeroth index, these are indices. Okay, so pardon if the spelling or something, there is some mistake spelling wise. uh, then what you will do, let's say the zeroth bit, first bit, second bit, third bit, and so on, is going till 32 31st bit. Okay, so here what you will be doing is, you will be mapping this zeroth index with the zeroth bit, first index with the first bit, second index with the second bit, third index with the third bit, and so on, ninth index with the ninth bit. Okay, so only this much range is required, and since it is well within the bounds of a 32-bit integer, I mean bit positions, these are bit positions. So why we are doing this mapping, you might ask. We are doing this mapping because for each number we will having two choices for each number in array. Either you will be taking it into the current subset, or you will not be taking it into the current subset. So these are just binary choices. Either you will be taking the number, or you will be not taking the number in the current subset that you are generating. So it is totally up to us. So let's say we decide to take A and we decide to skip B. We decide to take C and we decide to skip D. So it will be something like A, C. Okay. And if we go about in terms of indices, what it will represent, first of all, the third bit is set to be 0. If we are not taking something, then it means it is set to be 0. Second bit is set to be 1. First bit is set to be 0, and 0th bit is set to be 1. So if you take a binary representation, so it will be 1, 0, and then comes 2, and then comes 0 again. So these are bit positions. This is the 0th bit. This is the first bit. This is the second bit. This is the third bit. Okay. And if you take this binary number and have a decimal equivalent, you will get something. So this is 2 raised to power 0 into 1. Oh, okay, it will be 1 obviously. So, and this is 2 raised to power 2 basically. So it is 4. So the number that is it is representing is 4 plus 1 is equal to 5. Okay, so it is that simple. This is how each number from you can say 0 to 1 left shifted by size of the given array, minus 1 will represent all the configurations for generating all the subsets that can be possible for a particular array. What is this thing? 1 left shifted to size times. It is nothing but, first of all, let's say 1 is what? It is the 0th bit being set. Okay, so it is something like this. This is the 0th bit, first bit, second bit, third bit. Okay, and let's say the size of this array was 4. So here you might have seen that only 3 bits were required to represent, to map the indices of this array with bit positions in the integer. So in that case size will be 4. So when you will shift this 4 positions ahead, it will look something like this: 0 0 0, and then this will also be 0, third bit, and then this will be the fourth bit. Okay, you have just make it to jump 4 positions ahead. Okay, and when you will take one position less, so this bit will be unset. Okay, and this bit will have some configuration obviously. So you can say that you will be utilizing only this much, uh, because of this term, you can say, or the range end. Okay, so this is why we are using it. Okay, and 0 is in the case when you are not selecting anything. Okay, as per the definition also, there can be a possibility that you are not selecting anything, selecting possibly none elements from the array. Okay, so this is the whole thing that we will be using, and the concept, you can say. And let's have a quick look at the implementation. Okay, so this is the implementation. Let me quickly copy it to the board. It is not a lengthy one, so we can definitely take it to the board. So first of all, there will be different numbers in the range that I told you. This range from 0 to 1 left shifted by size minus 1 times. Okay, so these will be your masks for generating, or this will be storing whether you will be taking a certain index or not. And you might also ask that, okay, we will be these bits will be storing the position of index which is to be taken, then how come we will be able to know that we have to take that particular index? I mean, there should be some mechanism to, quickly check it. So what we will be doing is, let's say the index that we are checking for whether to include in the current subset or not is 0, or let's say it's 2. Okay, then initially you will be taking 1, which is the 0th bit at, then this is the first bit, then this is the second bit, and this is the third bit. Okay, now we are saying that we want the second bit to be set. Okay, so what you will be doing is, you will be left shifting this 1 to this position. Okay, and you are just left shifting 1 by 2, which is the value of the index. So it will look something like this: 3, then 1, then 0, and then 0. Okay, so this is the 0th bit, this is the first bit, this is the second bit, and this is the third bit. So it will form a certain, you can say, another kind of mask. And when, let's say, the index would have, it would have been something like 1 0 1. So this is the 0th bit, this is the first bit, this is the second bit. So when you will do a AND of these two entities, you will get this 0 0 and then 1 and then 0. So this is the binary representation that you will be getting, because only this bit is common in both of them. Okay, if we change the color here, so this bit is common in both of them, the second bit. So you will get it. So you can see that this is not equal to 0. So in case this, evaluation does not come equal to 0, you will come to know that, okay, you have to take this index into the current subset. So these index mask will represent nothing but the configuration or the elements that are needed to be in the current subsets. And how we are coming to know? Because each index is mapped with 1 bit. Okay, and turning on and off that bit means taking the element present at that index or leaving the element present at that index. Okay, so this is what we are doing essentially. And if the current index is to be included in the current subset, then you will include it obviously. And this is the power set, you can say, you will be returning, or the collection of subsets. Then you will add the current subset into the power set, and at last you will return your power set. So this is the whole logic and everything. And as far as time and space complexities are concerned, you might have guessed that the number of operations that would be required will be of order. I mean, for each element we will be having 10 two choices, either to take it into the current subset or not. So in total there can be 10 such elements. So it will be 2 raised to power 10. Okay, so 2 raised to power 10 for generating the amount of subsets, and then again you will be requiring a linear run through the array to check which indices are to be are included in the current subset. So again it will be multiplied by 10 because of the size of the array. Okay, so if we go in terms of code, so this one will be running around in worst case element, this array being of maximum size 2 raised to power 10, and this will run 10 times. Okay, so that's why we are multiplying these two terms, and it is very manageable. I mean, I think it is around 1204, and so it will be around 1. I mean, there are just, it is up to 10 raised to power 4 or something. Okay, and there is a limit for the number of operations, which is 10 raised to power 8 operations limit, and it is well within that limit. So you can say that your solution will be accepted, and this will be your time complexity. Okay, so 2 raised to power size into size. Size is the size of the given array. Okay, so time complexity wise it will be this. And as far as space complexity is being concerned, if you are not taking the arrays that you are using to build the result, so you can say it's pretty much constant extra space if you are not considering these things, this vector for current subset and this result array. Otherwise you can uh, you know definitely find out what will be the space complexity here as per the size of these. So this is what will be the complexities. If you are still having any doubts, please feel free to ask them in the comment section. I hope this solution walkthrough added some value to your journey of owning your DSA skills. And if you are still curious about or want to learn more about bit masking, then I will try to find an article on bit masking and I will include it into the description section of this video. And till then, keep solving problems, keep practicing, and I will see you in the next video. Thank you for watching.